Now I would like to discuss this problem of looping, and, and see what are its effect and how we can taken care of it, right? So again, look at another scenario, and here there are also loops in this table. For example, look at this path. The cost to reach from E to A via D. So what I'm saying is I want to go from E to A, but via D, right? So the cost reached from E to A via D is what? So this means E will first send message to D, and D's shortest path is via E, right? So this means there is a loop here, right? So this cost means the cost reached from E to A via D here involves a loop. Similarly, look at this cost reach from E to A via B. Again, I want to go from E to A, but I want to go from E to A via B. So first I'll send message to B, and B's shortest path is again via E. So again, we have a loop at E, right? So this means obviously this loop path is not the shortest path or the least cost path here. Um, but we need to see how we can address it. So by the way, before we move forward and discuss how these loops can create problems, so this distance table that we have just discussed gives us the routing table, right? So in routing table, for example, we have the destination and we have the outgoing link. So if I want to, and the cost associated with it. So if I want to go from E to B, the outgoing link is the link attached with router D. The next hop is router D, and the cost is 5, right? And similarly, if I want to go to reach destination C from E, the next hop is D, and the cost is 4. So this distance table is used to create the routing table to make a forwarding decision based on the least cost path. Okay, so uh, let's uh, let's see how the least cost change can create a problem and can result in a loop. So let's assume a sunny day scenario. There's a good news that the cost has changed from y to x to from 4 to 1. So what happens here is that at time t naught, we notice that the cost from y to x, y to x via x means x being the direct neighbor has been changed from 4 to 1. So obviously this is the new least cost, and as soon as y learned about this new least cost, it informs its neighbors. So it will inform its neighbor z that it has a new least cost, right? And immediately the neighbor z will say, okay, fine, the cost reached from me to y is 1, so 1 plus 1 is 2. So it also has the new least cost that is 2, and then it informs y about it. And after a couple of iterations, the algorithm terminates or is in a stable state. Okay, but look at the other scenario. What if the least cost has changed from 4 to 60? Then what do you think? Uh, how many number of iterations are required? Do you think that the algorithm terminates in a couple of iterations? No, right? So it's a bad news, and bad news travels slowly, right? So, for example, if you have been unable to pass a course, so this news takes a lot of time to reach your parents. So it's a bad news. But if it's a good news, you have topped in a course or in a semester, so you will immediately call your parents and friends and family friends to tell them that you have secured a good grades. So this can create count to infinity problem, right? How and this is because of the loops in the distance table, right? So let's see how. So look at this table of y uh, before this change. The cost reached from y to x. The y to x, y-x means x being the direct neighbor is 4. And I want you to understand this cost, right? And this cost is the cost to reach from y to x via z. The cost is from y to x via z. So this means if y has to send message to destination x, but via z. So what is this cost? 6. So this means y will first send this to z, and look at z's table. The cost to reach from z to x via y, which is the least cost, is 5. So this means z's least cost is via y. So this means the 6 means y will send a packet first to z, and z will again send it via y. So obviously, what is here? Yes, you're right. There is a loop here. Okay, a packet is visiting more than once to this node y, router y, and that's why we'll see this will create a problem here. This bad news. So at t naught, the y has noticed a change here. That the change is the cost has changed from 4 to 60, right? So immediately when this cost has changed from 4 to 60, it has selected the path which involves loop, right? So it immediately selects 6 as the shortest path. So it informs z that the new least cost is 6. So y is telling z that the new least cost is 6. So y says, okay, fine. The y is telling z that the new least cost is 6. So z is saying, okay, fine. The cost to reach from me to y is 1. So 1 plus 6 is 7. Again, z tells y that the cost to reach from me to x is 7. Right? The cost to reach from z to x y is 7. And y again says, okay, fine. What is the cost to reach from me to z1? So again, the cost to reach from y to x via z8. So because of this loop, 50 plus iterations in order to have the algorithm in stable state. And that's why we call it a count to infinity problem, right? So we have to do more iterations in order to select the right path, right? And the solution to this problem is Poisson reverse. We need to Poisson the reverse path, means the path involving the loop, right? So see, there is no reverse path here. So I have declared it infinity. Okay, and when we talk about RIP, because RIP makes use of this distance vector routing algorithm, RIP protocol. So what happens in RIP is this infinity is equal to 16. So if 16 is mentioned there because the maximum number of hops that are allowed in RIP are 15. So if I mention 16 here, this is equivalent to infinity, right? So what happens here? Now again, look at the same problem. That after t naught, there is a change in the link cost between y and x, and the cost has changed from 4 to 60. Okay, so immediately the new, and rightly so, the cost is selected, which is 60. And now it informs z that the cost has changed from 4 to 60, and it says fine. The cost reached from me to y is 1, so 1 plus 60 is 61. So it enters 61 here, but it rightly selects the least cost, which is the direct cost from z to x, and it informs y that look, the cost reached from me to y is what, 50, and y from me to x is 50, and y says, okay, fine. My cost from my cost to reach to z is 1, so 50 plus 1 is 51, right? So after, you can see, after 3 iterations, the algorithm will terminate, will converge if we Poisson the reverse path, and otherwise, because of the loop here, we had this count to infinity problem where we have to do a lot of iterations in order to have the algorithm in a stable state.